Okay, hey folks, let's go over these energy solutions for the Simple Harmonic Oscillator and talk about their properties. Let's do it. Find the right slide. Okay, so we have our specific solution, right? With our normalization constant, our Hermite polynomial, and our Gaussian term. We also have our displacement scale here. And so what we're going to do is plug all of this stuff in, and we're going to test if these solutions are acceptable by looking for an eigenvalue. So we're going to plug all this stuff back into our original Schrodinger equation and see if this gives us an eigenvalue. And for now, we're just going to try this for nu is equal to 0. But we should note that we really do need to also try this for nu is 1, 2, 3, 4, etc. And see what kind of a solution we get. So for the time being, we'll use nu is equal to 0. And if you recall, the Hermite polynomial for h, so when nu is equal to 0, is 1. So this is going to give us the easiest solution to test. And we're also going to put back in our x space. So we need to deal with that as well. Okay, so what we can do then is come up with the following. We can say our wave function of quantum number nu equals 0 of, that's going to be x is going to equal n of 0. We know the Hermite polynomial for nu equals 0 is 1, so we'll just leave that alone. And then that's going to be an e to the negative x squared over 2 alpha squared, right? So replacing my y's with the x and the alpha, okay? So now to plug this into the Schrodinger equation, we know that we're going to take the second derivative. So let's do that. And to make this easier, we're just going to keep this normalization constant with its symbolic moniker n there. So now taking the first derivative of this, we take the derivative of what's in the exponent, right? And that's going to come out in front, negative n sub 0. And then we're going to get an x over alpha squared all times e to the negative x squared divided by 2 alpha squared. And then now we need to take the second derivative, right? Because the operation tells us to take the second derivative of psi. So now we're going to have to apply our product rule. So first, we'll take the derivative of the x. So that's going to go as negative n over 0, and then the x drops out. And we've got 1 over alpha squared times e to the negative x squared over 2 alpha squared. And then now we'll take the derivative of the exponential portion. So the normalization constant stays. The x over alpha squared stays. And then now we're going to get an additional x over alpha squared from the derivative of what's inside the exponent. So, and we'll just keep that written as such so that we can keep track of everything. Okay, and then now that becomes our second derivative. So now we can plug all of that back into psi and keeping track of our constants. So we'll have a negative h bar squared over 2m. I'm going to plug in my solution here. And what I want you to note here is we could see our wave function was n times e to the negative x squared divided by 2 alpha squared. So every time I see that, I'm just going to replace that with psi of 0 to make this easier to write. And I'm also going to switch the order of these because I like having a positive term written first. So I'm going to end up with x squared over alpha to the 4th power. Okay, and then I have just, the normalization constant times e to the negative x squared divided by 2 alpha squared. So that just equals psi of 0. Okay, so then now I'll say minus, and I'll put this term in here. And we've got 1 over alpha squared and times the original wave function. Okay, so now we can say plus 1/2 times kf x squared. And let's see. Oh, how about that? I was missing a psi in there. Maybe you noticed that. Okay, there's supposed to be psi of x written there, right? The potential energy operator operates also on psi. So we'll just write that as psi of 0, and that all equals E times psi of 0. And we'll note here that this energy solution really is just for nu is equal to 0. Okay, so now we can distribute through our constants and collect like terms. And I'm going to do that by plugging in our constants for alpha to see if anything will cancel. So we have our negative h bar squared over 2m. And then now I'm going to have x squared times psi divided by alpha to the 4th power. Well, we recognize here alpha was given as the 1/4 power. So it's just going to be all those constants, but flipped. So you can see why now we preemptively scaled alpha to be to that 1/4 power for convenience. So now we got mkf over h bar squared times x squared psi of 0. Let me clean that x squared up just a little bit. Okay, so that's an x squared. Maybe that's slightly better, maybe not. Okay, and then minus, and then now we've got 1 over alpha squared, and that's all going to work out to be m to the 1/2 power kf to the 1/2 power all over h bar all times psi of 0. And then, of course, still plus 1/2 kf x squared psi 0 equals E0 psi 0. Okay, so now I'm going to distribute my constants through. So I can see that my h bar squared and h bar squared will cancel. My m and m will cancel. And so then I am left with negative 1/2 kf x squared psi of 0. Now distributing all of that through, my 1h bar is going to cancel with 1h bar, leaving me 1h bar left. And then the m to the 1/2 is going to cancel with that m to also give me an m to the 1/2, but on the bottom. So I'm going to end up with a plus h bar over 2 times kf over m all square root times psi 0. And then now I've got this plus 1/2 kf x squared psi 0 all equals E0 psi 0. So now you can see quite conveniently this term and this term will cancel, and I'm left with a pretty cool result. So I'm going to write that as h bar over 2, and I'll rewrite that as the square root of kf over m all times psi 0 equals E0 times psi 0. Holy smokes, look, we did it. We got the original wave function, and then now we can see we got an eigenvalue for energy. So I'm going to write that over here. We can see E0 equals 1/2 times h bar times the square root of kf over m. And let's remember what that looks like, because we're going to see some familiarity there. And so now, of course, the next thing to try would be to go for nu is equal to 0 and get the new Hermite polynomial and do this all over again. But recall, our H1 Hermite polynomial will give us a slightly more complicated term. So we'll get a lot more complicated here. But all the same, it will work out. And what we will find is we get the following. So we get a general solution for E of nu, which will go as the following. It will go nu plus 1/2 times h bar omega, where omega is the square root of kf over mu. So this time I put back that reduced mass, right? Recall that's m1 times m2 over m1 plus m2, right? For the situation when I have two masses on a spring. And so what's really cool about this is, if you recall, we got this from the classical mechanics. So this is our angular frequency of our oscillator, which we can see comes directly into our energy solution right there. So that is awesome. And now if we notice here, if we look at this, if we go back to our potential energy plot, and I've got that also over here on the side, we can see our solution. And I'm going to draw it a little bit better. This picture is not quite showing you the full truth, because remember, we imposed that we have to have these asymptotic solutions where psi falls off to 0 at large displacement. So that would be our nu equals 0 solution. Our nu equals 1 solution looks something like this. Our nu equals 2 solution looks something like this, and so on. And now if we were to calculate delta E of nu between any of those levels, we would find that it equals h bar omega, right? So if I take, for example, E at level 1, that's going to be 3/2 h bar omega. And E at level 0 is 1/2 h bar omega. So if I subtract those two, I just get h bar omega. And this is a really cool solution because it has the same form as our regular old energy equation. E equals h times nu, which equals hc over lambda. So this is pretty awesome that for such a complicated problem, we got such a simple solution. Okay, so I think that is all I'll say about this for now. So we will talk more about the properties of the simple harmonic oscillator and some realistic examples in the last video. I'll see you later.